All right, this is lesson number 24, posted on June 1st. This is the same day as test number 3. So I'm going to assume you've already taken the test, right? So after the test, we're going to start in on our last section, right? We only have one more week left. We have 3 more lessons, including today, okay? So the homework for this will be due on Friday, June 5th. Everything gets a little more compact just because we're kind of wrapping everything up, okay? So this is due June 5th. That's Friday. On Monday, June 8th, there's a quiz. The last homework set is also due. And then the final is Wednesday, June 10th from 2 to 4 p.m. on Sapling. I'll give you more information, but it's basically 60 points in 90 minutes. So a little bit longer. And so make sure you're getting ready and start reviewing this. Okay, so last time we ended up talking about buffers, right? We finished that off. And we said that a buffer is a weak acid, like HF, and a weak base, like F-. And so let's say we add in some base, some OH-, right? Well, OH- is going to react with one of these two, HF or F-. Well, which one? Because this is a base, it's going to react with the acid. So the OH- and the HF are going to react, and that's going to go ahead, and that's going to produce our F- and leave behind H2O. Okay, that's how buffers work. They remove any added extra OH- or H+. All right, and then we moved on to titrations. And titrations are when we add 2 solutions that react with each other. What we've been doing in lecture and also in lab is acids and bases. And so when acids and bases come together, we have what's called the equivalence point in titration. Equivalence point is important because this is the point where the moles of the acid equals the moles of the base. And we looked at that last time for strong acids and strong bases. So let's say I have a strong acid and I titrate it with a strong base. It's going to start at low pH, and pH is going to increase over time. And notice right around this red part, which is called the equivalence point, we see this huge increase in pH. Okay? At this point, moles acid equals moles base. If instead I have a strong base and I add strong acid, so my strong base is the analyte, and my strong acid, that's going to be my titrant. Well, what happens? In this case, I start at high pH because it's base, and then I add in acid so it decreases. Again, we have the equivalence point where moles of acid equals moles of base. All right, now let's go on to case number 3. Case number 3 is when I have a weak acid. Okay, that's what my analyte is. And I go ahead and I add in a strong base. The strong base, NaOH, can be my titrant. All right, so here's my weak acid. In this case, it's CH3CO2H. Now, instead of producing H+ like when we were talking about strong acids, the weak acid just is itself. And so when it reacts with OH-, right, it's going to go form that weak base plus H2O. Okay? Notice, I start off with a weak acid, and when I do this, I form a weak base. A weak acid and a weak base, that's a buffer, right? So when we do titrations of weak acids, we end up with a buffer. All right, so let's go ahead and let's look at a titration. Let's say we titrate 25 mLs of 0.1 molar CH3CO2H, my weak acid, and I'm going to add in my strong base, and it's going to be 0.1 molar. Okay, so when I do this, notice when I am initially doing this, so I have no NaOH added, I only have my weak acid. That's 0.1 molar. Okay, so 0.1 molar of my weak acid. I could go ahead and I could use an ice chart, because all I have right now is an acid, and I could figure out the amount of H+. Okay, notice not all of it dissociates because it's weak. And then I could go ahead and use that H+ to figure out pH. Okay, this is just an ice chart problem that you did for lesson number 21, right? And was on test 3. Okay? All right, but that's the boring part. Let's say in this titration, we're now part ways through it, and we've gone ahead and we've taken our weak acid, CH3CaO2H, and now we've added in some NaOH. And notice we've added in 10 mLs of 0.1 molar NaOH. Okay? So what I can do is I can do an ice table to figure out what's going to happen, right? So I have my CH3CO2H, and I'm going to add in OH minus. And this is going to go, this OH minus is going to steal an H plus from here. That's going to leave behind my CH3CO2 minus, my weak base. And then it's going to get me H2O, right? So what do I have initially? This is kind of like when we were dealing with buffers. We're going to look at how many moles of each I have, okay? So I have 0.1 molar times 0.025 liters. That's for my weak acid. So that's going to get me 0.0025 moles of my CH3CO2H. And then I'm adding in 10 mLs of my 0.1 molar NaOH. 10 mLs is 0.01 liters times 0.1. That's going to get me 0.001 mole of my OH minus. All right. At the beginning, I have none of my CH3CO2H. Okay? So what's going to happen? Well, just like we did with the buffer, all of this is going to react because there's less of it. It's the limiting reactant. And so if all of this reacts, 0.001 of this reacts, 0.001 of this also reacts. And then they form that much of this one. Okay, so that's going to leave me at the end with 0.0015 moles of my CH3CO2H. I'm going to have none of my OH minus. And what do I have? I'm going to end up with 0.001 of my weak base. I have a weak acid. I have a weak base. So what is this? This is a buffer. Right? So during titration of a weak acid, I end up with a buffer. And so I could use the Henderson-Hasselbalch equation, where pH equals pKa. We have our Ka at the very top, so I'm going to go negative log of 1.8 times 10 to the minus 5. Okay. Plus the log of base over acid. Always remember it's base over acid. This is going to get me 4.74. That sounds familiar. I know we've used this weak acid quite a bit. And then 0.001 divided by 0.0015, and I take the log of that. That's going to get me plus negative 0.18. Okay. I go ahead and I do this, and I get a pH of 4.56. Okay. Notice what's happened to my pH. If you look at the screen at the top, I started off at 2.87. I went ahead and I added some of the OH minus, and notice I got to 4.56. So the pH increased, not a lot, but still quite a significant amount. Let's go ahead and show this on the screen. Okay, so we go ahead, we figure out how much of our buffer components we have, right? Use pH equals pKa plus log of base over acid. And I end up with my pH. Okay, so my pH has increased from 2.87 to 4.57. But now that I have a buffer, right, notice this is a pretty big change. But now that I have a buffer, it's not going to change a lot. Okay, and so what we end up getting is when we titrate a weak acid with a strong base, we end up with a low pH. Why? Because it's acidic. We get a large increase at the start, and then once we have that buffer, the change actually becomes a lot smaller, right? So we have this region right here where the pH isn't changing much, right? We're going all the way from 5 to 15 or 20 mLs, and the pH is barely changing. This is called the buffer region, okay? Once we get to a certain point, we get out of this buffer region. This is where we get past the, remember, buffer capacity, and all of a sudden the pH starts changing. And now we get to the equivalence point. The equivalence point is an area, again, where we get this huge change, but now this is where moles acid equals moles base, okay? And so, notice where this pH is, right? The pH is actually above 7. That's because once we get the to this point, we have some weak base left over, and that's what causes a basic pH. Okay, halfway through this buffer region, we have what's called the midpoint. The midpoint, sometimes it's also called the half equivalence point, is when we get halfway to the equivalence point. So the equivalence point here is at about 25, so this is at about 12.5 mLs. And this is the part where we end up with the weak acid, the amount of weak acid we formed, HA, being equal to the weak base. Okay, that's because we've gone ahead and we've turned half of our acid we started off with into base. Okay, now at this point, seeing that we have a buffer and pH equals pKa plus log of base over acid. Well, if base and acid are the same, this becomes log of 1, which becomes 0. So at the midpoint, the pH equals pKa. That means for this acid, the pKa would be around 4.5. Okay, and then I could go ahead and I could find Ka. All right, so that is case 3. If I have a weak acid and I add in a strong base. Okay, notice this is similar to case 1 where we had a strong acid with strong base, but notice two things. First, we end up with this sudden increase that we don't see in case 1. Then we get to the buffer region. We don't see this big increase in case 1 when we have a strong acid. Also notice that where my equivalence point is. Here, it's at 7. Here, it's going to be higher because I'm going to be left with a weak base. Okay? All right, so this is for a weak acid and I add in a strong base. What happens if I had a weak base and I had in a strong acid? Well, I get basically the mirror image of it, right? So this was case 3 that we just did. Case 4 is going to look like this. I'm going to start with a high pH because I'm starting off with a base. My pH is going to decrease because I'm adding in an acid. And notice I still get this buffer region. I still have my equivalence point here. And at the midpoint, my pH is going to be equal to my pKa of the weak acid. Okay? And the equivalence point ends up being below 7, right? And that's because at the equivalence point, we have extra weak acid. Okay, so it ends up being acidic. Okay, so you should know how to differentiate between these 4 titration curves. We'll show them again in a little bit. And notice how the first 2 have the same reaction because it's a strong acid, strong base. In 3 and 4, it's a little more complex because my weak acid and my weak base don't fully dissociate, right? So my weak acid doesn't just produce H+, whereas my strong acid does. Okay? All right, case 5, and it's not one we actually will do many problems with, but this is when I take a polyprotic acid and I add in a strong base. So in this case, remember what polyprotic means. I have more than one acidic H+, right? So if I add a diprotic acid, I'd end up with 2 equivalence points. And notice right here and right here, these are 2 buffer regions. And I could look at the half or the midpoints, and that would give me my pKa1 and my pKa2. All right. We could also have a triprotic. Triprotic would have 3 of these. A tetraprotic would have 4 of those, etc. I've had biochemistry students, right? That's the merger between biology and chemistry, come in with these types of problems because once you get to things like proteins and even nucleic acids like DNA, you end up with multiple with polyprotic acids, right? So you have to deal with this there. All right, but we're not going to really deal with case 5 much here. Okay. We could also have a case where we use a weak acid or a weak base as a titrant. Remember, the titrant is the thing we're adding, right? Usually, or always, we should use a strong acid or a strong base as our titrant, okay? We don't use weak acids or bases. It just makes it way too complicated, okay? All right, so we have these 4 cases where we have either a strong acid or base being titrated with a strong base or acid, or a weak acid base being titrated with strong base or acid. Notice it's always acid plus base. I don't take a base and titrate it with a base. It's not going to work. And then we have case 5, which we're not going to really deal with. Okay, so these are our 4 types of titration curves. Okay, you should be able to, if you know it's strong acid, strong base, draw something out like this. Or if you visually see it, you should be able to say, oh, this is a strong base titrated with a strong acid. Okay? You can tell what the analyte is based on whether it starts off with a low pH or a high pH, right? If my analyte is an acid, right, such as in case 1 or 3, I start off with a low pH. If I start off with a high pH, like in 2 or 4, that means it's a base. All right, we have our equivalence point. The equivalence point is why we do titrations, right? And the equivalence point in all these cases actually are all at 25 ml, right? And the equivalence point is where the moles acid equals moles base. So this is the most important thing. For strong acid and base, if that's my analyte, it's going to be at pH 7. It's going to be greater than pH 7 if it's a weak acid. Sorry, this should be greater than. This should be less than. Let's go ahead and correct this real quick. All right, there it's corrected. If you have a weak acid, your equivalence point is going to have a pH above 7. If it's a weak base, it's going to be less than 7. All right. If you add something like a diprotic or triprotic, you'd have multiple equivalence points. All right. we have the buffer region if my analyte, what I start with, is weak. Okay? So for instance, a weak acid or a weak base, we start off with this buffer region. We don't see this for the strong acid and strong base. All right, and right in the middle of that, at the midpoint, that's halfway, right? This is at 25 mLs, so this is at 12.5 mLs. I can look at that and I can say, okay, my in this case, my weak acid will have a pH around 4.5 to 5, right? I need to look at the actual data. Okay, so let's do some problems with this. Let's look at this curve, okay? For the following curve, is the analyte a strong or weak acid or base? Remember, analyte means we're looking at the beginning, okay? So, notice my pH is high. That means I have a base. And notice how there's no huge drop at the beginning, okay? And that the equivalence point is right at 7. Okay? That means this is a strong base, okay? We could now use this in order to figure out the concentration of our NaOH, okay? So it tells me here that 40 mLs of our NaOH, that's our analyte, is titrated with 2.2 molar of our HCl. That's our titrant. And we want to know the concentration. All right, so what we're going to have to do is we're going to have to use this equivalence point. You can estimate it based on the curve, that volume, in order to find the concentration of our NaOH. Okay, this will be video problem 24A. All right, let's look at another one. Let's say we have this curve. And in this curve, we're asked, is our analyte, what we start with, a strong or weak acid or base? Well, it's an acid because it starts off at low pH. And notice we have this big increase at the very beginning. And then we have this gradual, right? This is our buffer region. So what that means is that we're starting off with a weak acid. Right? Okay. And notice that our equivalence point is also above 7, right? Here's 7. Our equivalence point is somewhere up here. Okay. All right, so now we want to know, based on this curve, we're told that 22 mLs of an acid, we don't know which, is titrated with 0.45 molar NaOH. Okay? So this is my titrant. So use the curve to figure out the volume of my NaOH, and then use that to figure out the concentration of the acid. Then use this value right here, right? That's my midpoint, to figure out the Ka of the acid. Remember, at the midpoint, pH equals pKa. But I'm asking for Ka. So to figure out Ka, I need to do 10 to the negative pKa. That's the same way that when we went from pH to H+, H+ equals 10 to the minus pH, right? So we can do that. Okay, that's video problem 24B. Let's go ahead and do one more problem. This one we'll do here, and that's because this is a little weird. Okay, so here we have a weak base and we're titrating it with a strong acid. So let's say I wanted to figure out the Kb of that weak base. Okay? All right, what do we know about the midpoint? The pH equals pKa of the weak acid. So what that means is, let's go ahead and do this on the board. Okay, so we have our curve here. So we want to know what the Kb of the weak acid is. So this point right here, which is my midpoint, this is the place where pH equals pKa of my weak acid. Okay? Well, we're not asked for that. We're asked for the KB. So we need to find the way to get from pKa to KB. All right. But first, let's go ahead and make sure we understand what this means. All right. So whenever we have a titration curve like this one, it's always pH versus ml added. So if I want to look at this point right here, I'm not going to look at the x-axis because this is mLs. I don't care about mLs, right? What I care about is I care about my pH, so my y-axis. So let's look at this. This is about, if I look at the screen, and I'm just estimating, it's about 9.5. All right? So my pKa equals 9.5. So how do I go from pKa to Kb? Well, what I have to do is I need to remember that Ka equals 10 to the minus pKa equals 10 to the minus 9.5. I do this on my calculator. I get 3.16 times 10 to the minus 10. That's my Ka. My Ka times my Kb equals Kw, which is 1 times 10 to the minus 14. So Kb equals 1 times 10 to the minus 14 over Ka. And that's going to give me 3.16 times 10 to the minus 5. Okay? Or, seeing that I started off with 2 sig figs, we'll just round this to 3.2 times 10 to the minus 5. Okay? That's my Kb, right? So I look at the chart, that tells me information on my weak acid, and I can get information on my weak base based on that. Okay? Okay, so here it is on the screen. We start off by estimating our pH at 9.5, right? You may have chosen 9 or 9.6, whatever. Plugging that in to find our Ka, and then using Ka times Kb equals Kw to find Kb. Okay. All right. So that is it for the main part of the titrations. I want to talk a little bit about another important part of titrations, that is indicators. So indicators, so titration is all about having an acid, adding a base, and so we're looking at a pH change. And so we can use pH indicators, which are chemicals added to titration, to help show that equivalence point. And they show it because they change color based on pH, right? For instance, this is litmus, which at 1 pH will be a reddish color. At another, it'll be purplish at basic conditions, right? So acidic, it's reddish. Basic, it's bluish. And this is what we have in litmus paper. Okay, why is this? Well, this is because litmus is actually this compound right here. Okay, that's why we call it litmus, because this is a very complex compound. And it ends up being a weak acid. Okay, and so what happens is, see this OH here? This hydrogen is acidic. So it can be lost, and we form this compound here. Well, this compound is red. This compound is blue. And so what happens is, because this is a weak acid base, right, what we have is equilibrium. So what we have is a Ka for this weak acid. So Ka is going to be this blue compound times H plus over this red compound. So what happens? Well, if I have acidic conditions, right, according to Le Chatelier's principle, so if I increase the amount of H plus, it shifts towards the left. So I end up with more of this litmus, which is red. If instead I have small pH or small H plus, which is the case in basic conditions, that means I don't have a lot of H+. So it's going to shift towards the right. And so I end up with blue color. And if I have neutral, that means, hey, it's somewhere between acidic and basic, so I end up with a purple color because I have some of this red compound, some of this blue compound. This is a good pH indicator if I want to tell if something is either acidic or basic. That's why we have litmus paper. There end up being a lot of different pH indicators, okay? They all have unique names because they have very complex structures. But we can see here all these compounds, right, change color based on pH, okay? So under acidic conditions, they may be a different color than under basic conditions, right? Let's look at one of these, methyl red. Methyl red, if you notice, right, it'll say it has this color change between 4 and 6 pH, okay? What that means is anything below this 4.2, it's going to stay red, right, like here. Anything above this, it stays yellow, like here. And then in between, it's halfway to red, halfway to yellow, so it's orange, okay? Now, this indicator, methyl red, so this actually looks something like this, right? We're just showing on that chart the place where it changes. But in reality, it has a different color based on pH. All right, so what this means is this would be a good indicator if I want to look at a pH change between 4 and 6, right? If I wanted to look for a pH change between 8 and 10, this would just go from yellow to yellow, so it'd be bad. But if I'm looking, hey, when does it go from 4 to 6? I could use the color change to do this. Okay? All right, and so we have all of these pH. And so if I have a titration like this one on the right, and I want to know when it gets to that equivalence point, right about here. What this means is I want something that will change from one color at pH 6 to a different color at pH 12, and preferentially around 9. Okay? So I can look at these and I can say, well, if I were to use this color or this one here, let's use this one, the dinitrophenol, right? It's going to have its color changer about 3. So it's not going to do me much good here. But if I use something that had a color change right around this 9, that would be good. So phenolphthalein would be a good choice. It would go from clear, right? Notice this shows it as white, but that's really clear. Clear to pink at this titration. So it start off at clear, and it get more and more pink as we go along. Okay, and when we first see that color of, or that pink color, we'd say, hey, our pH is, or we're at our equivalence point. Okay, all right. I say here methyl red. You know, this would be a bad choice because it would already change color right here. Okay. All right. So why don't you use this data right here to try to figure out these problems for video problem 24C, right? We want to know what is the color of bromothymol blue at pH 4? What's the color of ocresolphthalene at pH 8? And then methyl orange at H plus equals 1 times 10 to the minus 3. So you're going to have to convert that to pH. Okay? All right, and then there are some more problems here. All right, so pH indicators are a really useful thing. Instead of measuring pH, we can actually just look for a color change. You've used in class litmus paper or in lab. There are also universal pH paper that changes color based on pH. So instead of just changing from red to blue, it changes a multitude of colors. So if it's a yellow, that means it's 5. They are able to do this because there are different indicators on here, right? So they have a lot of indicators. Each one is going to give you a different color. For gardening, we also see this. If you had hydrangea and you plant them in acidic soil, you get this blue color. But if it's in basic soil, you get this purple color, right? This is an example of, hey, this color changing in nature. Okay, so that's it for titration part of lesson number 24. We went through 5 cases for titration. You should know these 4 definitely. Polyprotic, you really only need to be able to say, okay, if I have diprotic, I'll have 2. If it's triprotic, I'll have 3. And then we talked about pH indicators. The last thing I want to talk about briefly is just a few other things on acids and bases. Okay, so in chapter 14.4, we talk about salts. Okay, now remember what salts are. Salts are when you take an acid like NaOH and react it with HCl. You get NaCl plus water. If you had NaOH and HF, you'd get NaF. These are salts. Okay. Well, what does this mean? If I were to take this NaF and put it into water, because sodium, anything with sodium dissolves, I'm going to end up with F minus. Okay. Well, this F minus is a weak base. So adding a salt in there, I'll actually get a basic solution, right? And we can end up with different types of salts based on what it's made of, right? So for instance, NaCl comes from a strong acid and a strong base. So it actually gets you something that's neutral, okay? If you have a weak acid like HF and a strong base like NaOH, you end up with a basic salt. The reverse will get you acidic salt. And if you add a weak acid and weak base, you get something that's either one. Okay. All right. Finally, this is in chapter 15.2. We want to talk about a special type of acid and base. Okay. So in 2.15, we talked about a simplistic definition of acids and bases. Acids produce H+, bases produce OH-. In this class, we talked about Bronsted-Lowry. That's that acids donate H+, and bases accept H+. You should remember this throughout your chemistry career. This is a major thing when you talk even about nucleic acids like DNA. Hey, it's an acid, so you need to know what it is. Okay? All right. What we're going to talk about now is something called Lewis acids and bases. And these are named after Gilbert N. Lewis. That's the same guy who came up with Lewis dot structures. And what he said was that Lewis acids are a compound that accepts a pair of electrons, and Lewis bases are a compound that donates a pair of electrons. This is a little more general definition of an acid and base. Okay? Let's see what this means. Let's say I have NH3 and H+. Okay? And these two things come together to form what's called an adduct, NH4+. Okay? An adduct is when I have 2 or more compounds or 2 or more molecules coming together to form a molecule. Notice what happens. This base is basically donating these 2 electrons to the H+. Right? So this is a Lewis base because it's donating electrons. Lewis acids accept electrons. This is accepting those 2 electrons to form a bond. And what they form an adduct. Okay? All right, notice how this is kind of the opposite of what we said with Bronsted-Lowry, right? For bases, we said they accept H+, and for acids, we say they donate H+. Well, electrons are negative, so accepting an electron, something that's negative, is kind of like donating something that's positive, right? So I'm switching between electrons and protons, so I'm going from accepting to donating, right? All right, now it becomes useful because for Lewis acids and bases, we don't necessarily have to include H+, right? So let's say I have this, NH3 plus Ag+, coming together to form this adduct, okay? In this case, the NH3 are donating the electrons to this silver, okay? And I'm forming this compound that has a central silver molecule. This silver would be a Lewis acid, whereas the NH3, the ammonia, is our Lewis base. All right, we often see adducts in a lot of cases involving metals. Okay, so that central atom is typically a metal, and then the surrounding molecules we often call ligands. Okay? This is a branch of chemistry called coordination chemistry. You saw this in Chem 215 when we did an experiment where we had CoCl2, we mixed it together with water, and we got this compound, CoCl2 hexahydrate. So we ended up with something like this, right? That had a central cobalt, and all of these were ligands, okay? This is important for metals, but it's also important in nature. You know, some very important compounds like hemoglobin, which carries oxygen in our blood, are an adduct. There's my central metal, and I have this compound around it. Chlorophyll has a magnesium, and we have an adduct form with this compound around it. And vitamin B12 has a central cobalt. Okay? So Lewis acids and bases, even though we're not going to talk more about them here, they're really important once we get into looking at biological compounds. All right, so that is it for lesson 24. We talked a lot about titrations, but we also have some additional stuff you should know. And all of this will be on the homework, number 24, which is due Friday, June 5th. Okay? A reminder, homework 22 and 23 is actually due Wednesday, June 3rd. All right? With that, I will talk to you next time. Bye-bye.